Hi, this video is about how it's possible to activate level crossing protection systems with ETCS Level 2 and how some European infrastructure managers already do this. The video is based on my master's thesis that I wrote about the topic. First of all, an important definition in this video: the distinction between fail-safe and non-fail-safe level crossing protection systems, short LCPS. A fail-safe LCPS doesn't need to give a message about successful activation or protection to allow a train to move over the level crossing. This means by sending the command to activate, it is ensured that the level crossing is protected when the train is at the level crossing. Advantage is the very short warning time that is reachable if a safe activation method is used. The warning time is the time from activation until the train is at the level crossing. In Germany, protection systems equipped with traffic lights only and protection systems equipped with HF barriers can be fail-safe LCPSs. Non-fail-safe LCPSs must either report that they are activated or that the level crossing is protected before a train can be allowed to pass the level crossing. For example, it can be necessary that the level crossing is reported as cleared from road vehicles. Non-fail-safe LCPSs have longer warning times because the train has to be so far away from the level crossing at the time of activation that it is possible to bring the train to standstill in rear of the level crossing. In Germany, LCPSs equipped with full barriers and bystra, that's a connection of regular traffic lights, and a LCPS can only be realized non-fail-safe. In this video I will explain some ETCS functions that are important for further understanding. However, I will not explain the basic functionality of ETCS here. If you're not familiar with ETCS, I recommend to familiarize yourself with it first. ETCS has since baseline 3 a function to prevent a train passing an unprotected level crossing unhindered, the packet 88. Inside of the packet, the following variables get transmitted to the train. In NID packet, the type of the packet, it's packet 88, so 88. In QD, the direction for which the packet is valid. In L packet, the length of the packet. In Q scale, the resolution of the length scale. In NIDLX, a number of the level crossing is transmitted to enable the onboard unit to reference a packet 88 with changed information to the correct level crossing to replace the information from a previous sent packet 88. This can be relevant if the level crossing first is unprotected but later protected, so the packet 88 is sent twice with different information. In DLX, the level crossing start location is transmitted. This can be depending on the infrastructure manager, the edge of the road, or a marker board in rear of the level crossing. In LX, the length of the level crossing is transmitted. This is the distance from the level crossing start location up to the end location where the restriction for an unprotected level crossing shall end. Most infrastructure managers use either the middle of the road or the second road edge. In QLX, status is transmitted whether the level crossing is protected or not. If QLX status is 1, the level crossing is not protected, and the symbol for the non-protected level crossing is shown on the driver-machine interface to the driver, and a restriction is effective. The speed which shall be supervised if the restriction is effective is transmitted in the variable VLX. In QStopLX is transmitted if a stop in rear of the level crossing shall be supervised, and in LStopLX in which area the stop shall occur. And why do we want to change the activation at all? Today, most LCPSs are activated by trackside sensors. The sensors can be induction loops, track circuits, or wheel sensors, also called treadles. If the sensor for activation detects a passing vehicle, the LCPS activates. But trackside sensors for activation have several disadvantages. It is additional trackside hardware, it must be installed, the correct installation must be proved, and the sensor must be maintained. Cables are necessary for connection to the sensors. The length of the cables can reach several kilometers if the maximum speed is high. And for track works, it can be necessary to remove and reinstall the sensors. At level crossings with non-fail-safe activation, it must be ensured that the train cannot pass the level crossing until the level crossing is protected. When using ETCS, a braking curve up to the level crossing is effective until the level crossing is protected. The problem with this is that the ETCS braking curves can be flatter so that the braking application point, shown here with the vertical thin blue line, lies at an earlier location than with conventionally defined braking distances. The brake application point would be in rear of the activation point. A train with such a braking curve would have to brake also if everything works correctly. To solve the problem, it is possible to move the sensor for activation further away from the level crossing, but this will result in longer running times for all trains. At level crossings with non-safe activation, which must be used for non-fail-safe LCPSs, it's therefore the objective to activate the LCPS so that the level crossing protected message reaches the train immediately before the train reaches the braking application point, so that neither the LCPS is activated for longer than necessary, nor the train must brake because of the braking curve. At level crossings with safe activation, it must be ensured that the command activate is never given too late. This implies that the time of activation must be calculated safely depending on the further movement of the train. The ETCS onboard unit offers especially two messages: the position report and the MA request. The position report is sent from the onboard unit to the RBC. As the name suggests, it contains the position of the train. The position is given in relation to the front end of the train. It also contains the localization inaccuracy. This means how much further and how much further back the train can be within a certain confidence interval. From the inaccuracy results additionally to the estimated front end, the minimum and the maximum front end, the speed of the train, the status of the train integrity, the current level, and the current mode are also transmitted. The position report is sent along with most messages. In addition, the RBC can request the onboard unit to send position reports cyclically, depending on distance or time. The MA request is sent prior to the end of the MA, so the RBC gets to know that it should send an extended MA to the train so the train can proceed unhindered. There are also MA requests for other reasons. The graphic shows how the MA request works from SRS 360 onwards. Before the brake application point, which is the perturbation location at the start of the indication curve, the onboard unit sends an MA request to the RBC at the time defined in the variable TMAR before this point. The time TMAR is necessary because the RBC needs time to generate and transmit an extended MA, and if the route is not already set, this must happen as a prerequisite, which can take considerably longer, especially if there are turnouts. In the older versions of ETCS up to SRS 340, the MA request was slightly different and not so clearly defined. In SRS 340, there still exists the pre-indication curve, which has been removed in SRS 360. A train according to SRS 340 sends an MA request at the pre-indication location, which is calculated to the end of authority, but not at the pre-indication location, which is calculated to the supervised location. This is a problem if the end of authority and the supervised location are close to each other, because the braking curves calculated for the supervised location are supervised with the maximum front end, but for the end of authority with the estimated front end. To solve the problem, the trains equipped in Denmark according to SRS 340 deviate from the ETCS specification and also send an MA request at the pre-indication location calculated for the supervised location. This is also the way how it is solved in SRS 360. Because the pre-indication was dropped, now the indication curve is used to calculate the perturbation location. The perturbation location corresponds to the indication location and is calculated to both the end of authority and the supervised location. Because the indication curve beginning from SRS 360 is steeper compared to the pre-indication curve in SRS 340, a 360 train sends the MA request slightly later than a 340 train with the same parameters will do. Because the MA request depends directly on the braking curve of the train, the MA request is well suited for the non-safe activation of a LCPS. Several infrastructure managers already have such solutions in operation or are about to deploy them. In Sweden, Trafikverket has a solution with non-fail-safe LCPSs in operation and a solution for fail-safe LCPSs which is not yet in operation. The solution for non-fail-safe LCPSs is based on the MA request. The solution for fail-safe LCPSs also uses the MA request, but the activation time is calculated based on the position report that is sent along with the MA request. In Denmark, Banedanmark has a solution for level crossings, which are all protected by non-fail-safe LCPSs, and a solution for passenger and staff crossings, which all are protected by fail-safe LCPSs, also called passenger warning system. The MA request is used for the activation at the level crossings. At the passenger and staff crossings, the activation is done conventionally using the track vacancy detection, but with a delay, which at some passenger and staff crossings depends on the maximum speed reported by the train. This refers to the systems in the western part of the Danish ETCS project, which are from Thales and Pinch. I have no current information about the activation of the ETCS-controlled level crossings in the east. In Norway, Bane NOR uses the position report for activation of the, as in Denmark, all non-failsafe LCPSs. The LCPSs of ProRail in the Netherlands are failsafe. The position report shall be safely evaluated for activation. In the following I will present the individual solutions. Depending on the infrastructure manager, there was a different amount of publicly accessible information of various kinds. For example, test cases for ETCS system compatibility, articles or operational rulebooks. However, this was not sufficient to really understand all the solutions, so I had to request the missing information from the infrastructure managers. Almost all of my questions were answered. Many thanks to everybody who helped me. To visualize the individual solutions in a comparable way, I have created sequence diagrams. The shown systems are always the same. The train, which includes the ETCS onboard unit, the RBC, the radio block center, the interlocking, the LCPS, the level crossing protection system, and the TMS, the traffic management system. The train has an interface to the RBC, which is specified in the ETCS specification. The RBC has an interface to the interlocking. The interlocking has an interface to the LCPS, and the interlocking has an interface to the TMS. And at some infrastructure managers, the RBC has also an interface to the TMS. It's important to know that all is based on information which I have gathered. Nobody has checked this. There can and probably will be errors and deviations from the actual solutions. It's also partially based on the requirement specifications of the infrastructure managers, which do not necessarily describe the solutions in every detail. In Sweden, TrafikVerket uses the MA request in the variant for non-safe activation of non-failsafe LCPSs. The different time required to reach the protected state, depending on the level crossing, is taken into account by different values of TMAR. There's no further optimization. First of all, the TMS commands the interlocking to set the route over the level crossing. The interlocking sets the route and reports this to the RBC. It's reported usually by transmitting a virtual signal aspect to the RBC. Now the RBC can send an MA up to the level crossing to the train. This MA up to the level crossing is necessary to trigger an MA request, because a packet 88 with active restriction is not sufficient for trains up to SAS 340 to trigger an MA request. When the train reaches the location where the MA request is sent, the train sends an MA request to the RBC. When the RBC receives the MA request, the RBC sends an MA across the level crossing with a restriction from packet 88 to the train, and at the same time it commands the LCPS to activate. The command is sent to the interlocking, and the interlocking forwards it to the LCPS. The LCPS activates, and when it has reached the protected state, it reports this to the interlocking forwards this to the RBC, and the RBC now can send another packet 88 without a restriction, so the train can pass the level crossing unhindered. The interlocking commands deactivation when it detects through the track vacancy detection system that the train has passed the level crossing. There is a second method for deactivation, not shown in the sequence diagram, which uses the position reports. When the train has passed the level crossing with the maximum possible train length, the RBC commands deactivation. However, the second method is only a fallback method, in the case deactivation by trackside detection has failed. At Bane Denmark, they originally wanted to solve the activation in a similar way to TrafikVerket. However, it's not always possible to transmit the changed value of TMAR to the train in time because of the closely spaced level crossings in Denmark. For this reason, TMAR has been set to a constant value of 50 seconds, and the traffic management system subsequently delays the activation by the remaining time. This time is configured for each level crossing, depending on the time necessary to reach the protected state. The solution described only applies to the western part of Denmark, which is equipped by Thales. As a prerequisite, a route is set up to the level crossing, and the train has a corresponding MA. When the train reaches the calculated location where the MA request is sent, the train sends an MA request to the RBC. The RBC forwards the MA request to the TMS. Then the TMS commands the interlocking to set the route over the level crossing, and at the same time it starts the delay which is configured for the level crossing. When the interlocking has set the route, it reports this to the RBC. The RBC then sends an MA across the level crossing, but with a packet 88 which contains a restriction. When the delay expires, the TMS commands the interlocking to activate the LCPS. The interlocking forwards this to the LCPS. The LCPS activates, and when it has reached the protected state, it reports this to the interlocking. The interlocking forwards this to the RBC, and the RBC can send another packet 88, this time without restriction, to the train, so the train can move over the level crossing unhindered. When the interlocking detects by the track vacancy detection system that the train has passed the level crossing, it commands to the LCPS to deactivate. At Bane NOR in Norway, as in Denmark, all LCPSs are non-fail-safe. For the ETCS-based activation, the position reports are evaluated. When the RBC detects, based on the position reports, that the train has reached a certain location, the LCPS activates. To adjust the activation location to the braking curve of the train, the location is calculated based on the current speed of the train. In future, it's planned to take the actual braking capabilities of the train into account. The TMS commands the interlocking to set the route over the level crossing. The interlocking sets the route and reports this to the RBC, so the RBC can send an MA with a restriction from packet 88 to the train. When the RBC detects, based on the position reports of the train, that the train has reached the calculated activation location, it commands the activation of the LCPS to the interlocking. The interlocking forwards this to the LCPS activates, and when it has reached the protected state, it reports this to the interlocking. The interlocking forwards this to the RBC, and the RBC sends another packet 88 to remove the restriction. The train can now move over the level crossing unhindered. For deactivation, the LCPS has an exit counting section. The state of this section is reported to the interlocking. When the interlocking detects, based on the reported state, that the train has passed the level crossing, it commands the LCPS to deactivate. Banedanmark has a second solution that is used to activate the fail-safe passenger and staff warning systems. The activation is based on the track vacancy detection and thus on conventional trackside hardware, but there's no additional trackside hardware necessary because a delay time is used, which at some level crossings also depends on the reported maximum speed of the train. First, the TMS commands the interlocking to set the route over the level crossing. The interlocking then requests the maximum speed of the approaching train, Vmax train, from the RBC, and at the same time it sends the announcement for activation to the LCPS. The LCPS then reports back that it is ready to activate, and the RBC reports the maximum speed of the approaching train to the interlocking. If all conditions for the route are fulfilled, the interlocking can report to the RBC that the route is set. The RBC then sends an MA to the train, so the train can cross the level crossing unhindered. When the delay time expires, the interlocking commands the LCPS to activate. The LCPS is deactivated in the same way as at level crossings in Denmark. The interlocking detects the passage of the train based on the track vacancy detection system, and then it commands to the LCPS to deactivate. ProRail safely evaluates the position report for the all fail-safe LCPSs in the Netherlands. The train periodically sends a position report to the RBC, usually every 5 seconds in message 136. Based on the distance from the level crossing, the maximum speed and current speed in combination with the maximum expected acceleration, the RBC can calculate the minimum time required for the train to reach the level crossing. From this, the RBC subtracts the minimum running time projected for the level crossing and obtains the remaining time until activation. In the graphic on the left, this is labeled T-order. When T-order has expired, the RBC commands the activation. The calculation is repeated with every position report. Because of the decreasing uncertainties, the activation time is always slightly later. In the sequence diagram, the TMS commands the interlocking to set the route over the level crossing. The interlocking sets the route and reports this to the RBC. The RBC then calculates the activation time of the level crossing for the first time, and issues an MA to the train. The calculation is repeated for each subsequent position report. When the activation time is reached, the RBC commands the activation of the LCPS to the interlocking. The interlocking forwards the command to the LCPS, which activates. The interlocking detects by the track vacancy detection system that the train has passed the level crossing and commands the LCPS to deactivate. For activation of the fail-safe LCPSs, Verket also uses the position report, but not periodically as ProRail does. Instead, an MA request is triggered in rear of the level crossing, and the position report sent along is used to calculate the delay time to activation. In Sweden, even for fail-safe LCPSs, there is a requirement that the train is braked in rear of the level crossing in case of failure, but does not have to come to standstill. This requirement has been implemented by issuing the MA over the level crossing with a time limit after calculating the activation time. The time limit expires shortly before the train can reach the level crossing. If the level crossing is regularly protected, an MA without a time limit is issued before the time limit expires. However, if the level crossing fails to be protected, the time limit simply expires and the train is tripped. The route setting works the same way as with the non-failsafe LCPSs of Verket. The TMS commands the interlocking to set the route up to the level crossing. The interlocking sets the route and reports this to the RBC. The RBC then sends an MA up to the level crossing to the train. When the train reaches the location where the MA request is sent, the train sends an MA request to the RBC. With the position report always sent along with an MA request, the RBC can calculate the activation time. The RBC now issues a time-limited MA to the train so that the time limit expires shortly before the train can reach the level crossing, and the level crossing should be protected at this time. The time-limited MA does not contain a restriction from packet 88. When the activation time is reached, the RBC commands the activation of the LCPS to the interlocking. The interlocking forwards this to the LCPS. The LCPS activates, and when it has reached the protected state, it reports this to the interlocking. The interlocking forwards this to the RBC, and the RBC sends an MA over the level crossing without a time limit to the train. So the train can continue to cross the level crossing unhindered. The deactivation works in the same way as with the non-failsafe LCPSs of Verket. These were the solutions I know for activating LCPSs with the ETCS Level 2. The solutions are very different, but none of them requires additional trackside sensors. Because all depend in some way on the speed of the trains, the warning time is more constant. But because of system delays, the warning time will be slightly longer compared to activation with trackside sensors that is optimized for the speed of the train. Because in all solutions there is no hardware in the track that is adapted to the operation and the speed of the trains, the operation and the speed can be changed without physical adjustments. Here are two more sources for graphics that I've not already added. I'll link some content-related sources and further reading material in the video description. Thank you for watching. I hope this was all fairly understandable. Bye.